Hello everyone, thank you very much for tuning into my talk. My name is Thomas Choi from the University of Southern California. Today I'll talk about a paper titled Co-located versus distributed versus semi-distributed massive MIMO, measurement-based evaluation, which is a topic related to the trending cell-free massive MIMO or distributed massive MIMO. Thanks to many researchers in the domain of massive MIMO has become a reality. Many 5G wireless providers, including Samsung, Nokia, Ericsson, etc., have developed massive MIMO base stations with antennas co-located in one box, which can be deployed to replace the legacy base stations with fewer antennas to augment both the spectral and the energy efficiency. With such progress, many researchers are now looking into other massive MIMO-related research topics, which are summarized in reference 3 by Professor Johnson and others. One of the research topics discussed for the future of massive MIMO is cell-free massive MIMO, where the base station is distributed as multiple access points, APs, or remote radio heads to various locations to prevent performance losses at the cell edges. These APs are connected to a central processing unit, which conducts signal processing for multiple users as introduced in reference 4 by Professor No and others. Answering the question of how many APs do we need and how many antennas per AP do we need are critical questions, especially in terms of deployment to maintain the optimal performance of cell-free massive MIMO system while maximizing the usage of frontal resources and overcome physical limitations coming from the installation of the APs, as well as connection and synchronization of multiple APs. It is also important to realize the system and verify the performance based on real channel data. In this talk, we'll compare 3 different base station antenna distribution methods. If we define variable M to be total number of base station antennas, L to be total number of APs, and N to be the total number of antennas per AP, the co-located system is a typical massive MIMO system with all base station antennas at the same location, L is equal to 1. The fully distributed system is the distributed antenna system where each AP is equipped with a single antenna, N is equal to 1, and the semi-distributed system lies in between these 2 extreme cases. We define a sample of large M times large K channel matrix between the base station and the user equipment as follows. Parenthesis MLK represents the specific system topology, while small s is the index of a sample. For example, if MLK is equal to 844, such system is a semi-distributed system with 8 total base station antennas, 4 AP locations, 2 antennas per AP, and 4 single antenna UEs. The channel will be 8 times 4 matrix, where each 2 rows of the same AP location will share the same large scale fading. To generate the channel data, which will be used to compare the system performances of various base station antenna distributions, we used a simple vector network analyzer-based channel sounder. If you aren't familiar with what a channel sounder is basically a RF system to evaluate wireless channel characteristics in a selected environment. Vector network analyzer-based channel sounder, which is slow in terms of measurement speed and has limitations on range due to having the transmitter and the receiver at the same box, can be easily operated and provide accurate channel information. The channel sounder is configured as follows. The transmitted signal is amplified, which is connected to 1x8 switch through 25 feet long cable. The 8 RF output ports of the switch are connected to 8 ports of the linear antenna array, which is shown on the right. The array has 4 radiating elements in the middle, while the 2 elements at the left and right ends were just used as dummy elements terminated to 50 ohm loads for consistency in antenna patterns. Each element contains 2 polarizations, one vertical and one horizontal, marked in blue and green. The propagated signal from the transmitting antenna will pass through the arbitrary wireless channel, then to the receiving antenna array, which is identical 8-port array as the transmitting antenna array. This antenna array is also connected to 8 times 1 switch at the receiver end. The signal then goes through another 25 feet cable to reach the bandpass filter, attenuator, and the amplifier before reaching the receiver of the VNA. The timing of the switches for both the transmitter and the receiver are controlled through a Lavie program in combination with digital TTL signal, which is also synchronized to the timing of the vector network analyzer. One measurement round per frequency point therefore provides us with 8 times 8 channel matrix. In terms of frequency samples, 1601 frequency points were used for 3.3 to 3.7 GHz frequency band. In this presentation, we consider measurement at every different frequency point to be different sample, although the performance may vary a little bit between frequencies within the selected 400 MHz band. The measurement campaign was conducted in an ultra lab facility in the University of Southern California, as seen on the photo on the right. The lab is 6 meters times 6 meters area, resembling a small factory setting with many metallic objects, walls, and blockages around the room. In order to extend the 8 times 8 point-to-point MIMO channel measurement data from a single measurement round to 64 semi-distributed massive MIMO measurement data, 64 measurement rounds were conducted in the following way. We first fixed a transmitting array acting as AP at one location and moved a receiving array acting as a UE to 8 different locations. Then the transmitting array was moved to the next location and the procedure repeated, measuring channels for all combinations of 8 AP locations and 8 UE locations. Because there are 1601 frequency points, we'll have 1601 samples of 64 times 64 matrices. As we can see, some APs had line of sight pass to some UEs, while other APs had no line of sight pass. The array used as AP was stationed at 2 meter height, while the array used as UE was stationed at 1 meter height. Because the channel is static in an indoors environment and no one was present, the channel coherence time was technically infinite, justifying our long measurement time. However, there is a weakness to this measurement campaign. While the semi-distributed massive MIMO case where M is equal to 64 can exist, assuming there are 8 AP locations and 8 antennas per AP, the largest co-located MIMO and fully distributed MIMO cases we can assume are M equal to 8 due to size of the antenna array, as well as difficulty in moving the antenna arrays to many different locations. Because this prevents comparisons of various base station antenna distribution methods in massive MIMO scenarios with large M, we also decided to use synthetic channel data if the synthetic channel data can provide consistent results with the measurement channel data. The synthetic channel data were produced in the following way. We again assumed 6 meters times 6 meter setting and predefined 64 candidate locations for the APs at the edges. The maximum number of base station antennas were assumed to be 64. For simplicity, we ignore shadowing correlations between the APs as well as small-scale correlations among antennas within the same APs. For the co-located case where L is equal to 1, we randomly picked a location out of the 64 candidate locations and assumed all the base station antennas are at the same locations sharing the same large-scale fading, while only the small-scale fading was varied between antenna elements. For the semi-distributed case where L is greater than 1 and less than M, we randomly picked several locations for APs. In this example, the number of APs selected is equal to 4, and we assumed M divided by 4 antennas were at each of the 4 AP locations. Each AP had varying large-scale fading depending on the distances between the UEs, while varying in small-scale fading for the antennas within the AP. For the fully distributed MIMO case, all the AP locations were used equipped with single antenna. For the UEs, 4.5 meters times 4.5 meters boundary was created for a 1.5 meter protection radius between the APs and UEs, and the single antenna UEs were located at random locations within the boundary. Again, we ignore shadowing correlations among the UEs during the multi-user MIMO analysis. The performance metrics we will use to analyze various base station antenna distribution is achievable downlink spectral efficiency. As we know, such spectral efficiency for a UEK for a sample S in a multi-user MIMO scenario can be written in the following way. Log2, 1 plus signal to interference plus noise ratio at UEK for sample S. The signal part, which is the numerator of the SINR equation, consists of normalized precoding vector from all base station antennas for UEK multiplied to channels from these base station antennas to UEK multiplied by transmit power from base station antennas for UEK. This interference part, which is the first term in the denominator, consists of addition of precoding vectors for any UEK apostrophe other than UEK multiplied by channel vector to UEK multiplied by signal power for UEK apostrophe plus the noise term at UEK. For the precoding, we use the maximum ratio transmit MRT and zero forcing. Maximum ratio precoding matrix is just the complex conjugate of the normalized channel matrix to maximize SNR, while the zero forcing matrix is that conjugate matrix multiplied by inverse of the transposed normalized matrix times conjugate normalized matrix to minimize the interference. Here are the CDFs of the spectral efficiency per UE in both the measured and the simulated scenarios, where the total number of base station antennas M is equal to 8 and the total number of UEs K is equal to 4. When we are using the MRT, it is hard to see much distinctions between the different antenna distributions. Also, the performances are not good due to having high interference term. However, the differences in performances are much more evident and the performance improves drastically in the zero forcing cases. First, let's compare different antenna distributions which are distinguished by the color of the plots. We want to look at the 95% likely achievable rate, which is a measure for coverage. So if we look at where the CDF is equal to 0.05, we see that the fully distributed graph is the best as expected, skewed most to the right. This can be explained by a higher chance of having at least some APs with the best channel condition in proximity due to distribution of base station antennas to multiple locations. As the number of the APs reduces, the 95% likely achievable rate becomes worse, as if the channel between a single AP and UE is bad, having more antennas at the same AP cannot help much. In contrast, in terms of peak spectral efficiency where the CDF is equal to 0.9 or more, the co-located performs the best, while the fully distributed performs the worst. The semi-distributed cases lie in between, having better 95% likely achievable rate than the co-located MIMO, while having higher peak spectral efficiency than the fully distributed MIMO. While the measured case with thicker plots and simulated case with thinner plots do not overlap exactly, the trends of the plots are like one another. After verifying that the trends of the measured plots and the simulated plots are similar, we now look at just the simulated scenarios where the comparisons of different base station antenna distributions at larger M is possible. The graph shows that at any M, there is semi-distributed configuration which can perform similarly to fully distributed case in terms of 95% likely achievable downlink spectral efficiency. This means that the number of APs may be reduced and still achieve similar coverage as long as the total number of base station antenna is similar. The last graph, it fixes the total number of base station antennas to 64 and vary the number of AP locations. As we see here, the 95% likely achievable downlink spectral efficiency when the number of AP is 16 is similar to where the number of AP is 64. We can reduce the number of locations for AP by a factor of 4 and still attain the similar coverage while having the better peak spectral efficiency. To wrap up my talk, due to many uncertainties in the deployment of cell-free massive MIMO, it is important to explore various types of base station antenna distribution methods, especially how often and how many antennas we distribute per area. And from measurements as well as simulations, we show that the semi-distributed massive MIMO can have similar coverage to the fully distributed MIMO and must be discussed further to optimize the future cell-free massive MIMO systems. And for future works, we hope to continue this effort in various settings with faster time domain measurement techniques. With that, I would like to thank everyone for listening to my talk, and here are the references from earlier slides. I'll be happy to take any questions throughout the conference, and you can email me as well if you have any further comments.